Mars. So before I answer the question of when will we find life on Mars and how, I'll just sort of outline why we want to look for life. So one of the fundamental questions that everybody wants to know is whether life arose on a different planet, and if it arose on a different planet, then it could potentially have arisen elsewhere in the solar system or in the galaxy or in the universe indeed. So why exactly do we want to go to Mars? Well, Mars is the closest and probably the only place that we can easily visit with our current technology. So at the moment we have several space probes that have been to Mars, but we have yet to have returned a sample from Mars. However, we do have pieces of Mars. So we have pieces of Mars similar to this. This is actually a meteorite, a piece of the primordial solar system, which would have accreted about 4.6 billion years ago. We have pieces of Mars, but because they were of the mechanism of formation, we don't know where on Mars they're from, or whether they're from somewhere where life could have existed, or even whether life could have existed at the time the meteorite was formed. If life did exist in the piece of the Mars meteorite that was formed, it's been like blasted off Mars, it's been heated to thousands of degrees, it's then hurtled through the vacuum of space and then plunged through our atmosphere. So even if there was life existing in this meteorite, we wouldn't know because the evidence of life was probably destroyed. So that's some of the outline. So how will we find life on Mars and when? So I'll start by saying when, and I'll be quite bold and say we will find life on Mars in 2030, and this is how we're going to do it. So we already have rovers on Mars. This is the Curiosity rover. This is the rover that I work on. It's a nuclear-powered, laser-wielding robot with various instruments in it. It's probably, at present, the most sophisticated scientific instrument that we've sent out into the solar system. It's powered by a 4-kilogram lump of plutonium, which sits in the back here, which then powers a whole host of scientific instruments, including some not-so-fancy cameras, which can actually tell us about the environment which the rover's in. We can take pictures of rocks and learn how the rocks were formed. And then in here, it has an instrument called the SAM, Sample Analysis at Mars, which is able to ingest rocks that the rover drills using its robotic arm. It then pours the rock sample into the body of the rover, and then it's got 4 separate spectrometers in there which are able to sort of digest the rock, heat it up, and then evolve gas, which can then be analysed by gas chromatography mass spectrometry to tell you what exactly is in there. So unfortunately, with this instrument, despite the fact that it's the most advanced automated mass spectrometer ever produced and flown into space, it's not quite able to tell us whether there is life on Mars. It has actually told us whether life could have existed. So at the moment, the instrument has told us that the molecules which could have then gone on to form life exist on Mars. So things which could have made amino acids, then gone into sort of long chain proteins and so on and so forth. So we have the ingredients for life on Mars, but we don't quite know whether life on Mars existed. And the reason is because Mars has no atmosphere. Lots of UV rays come in and bombard the surface. The UV rays actually penetrate quite deep into the soil, and if there's any complicated molecules that were there, they've been broken down by these UV rays, and then as a result of this, we haven't been able to find out whether there has been life or not, or there's no direct evidence of life yet. But Curiosity, which is currently in Gale Crater, so the reason why we went to Gale Crater is because from satellite images is that we saw loads of things called phyllosilicates or clays. Clays typically form in water, and water is an important chemical reagent for life. So, for example, all of our bodies are somewhere between 80 or 90% water. Water is probably the most critical or most important universal solvent because it will dissolve many different things. It's basically the medium which life will sort of form in. So NASA's mantra back in sort of the early 2000s when they sent the MER missions was follow the water. If you follow the water, you'll find a habitable environment, and then when you find the habitable environment, then you can start looking for life. So my role within the mission is sort of following the water to find the habitable environment. So Curiosity landed here in about 2009, and since then has discovered evidence of long-lived lakes. So as a geologist, I was quite excited to see these images. They look relatively boring, but if you look to the untrained eye, but if you look sort of in here, you can see that you have these millimetre thick laminations, and you see these similar things on Earth in the rock record and also in the bottom of lakes. So when we saw these rocks, we knew that we had found a lake, which is an ideal place for sort of having a crucible for forming life. Also as well, we found these rocks here. These are evidence of rivers flowing into the lakes. So you see here you have these surfaces sort of inclined in this direction, which means that the river was flowing that direction, and the river was flowing into Gale Crater. So we have a nice pond of water, which is a big reaction medium, and then you have rivers flowing in, bringing in various different minerals and other goodies which could be sort of used to create sort of a soup where life could eventually potentially have evolved. So this is actually what Gale Crater may have looked like about 3.6 billion years ago. So it's the sort of place you could imagine going and having a picnic. You could sort of lie down here. It kind of looks almost like it could be Earth-like, sort of a lake, maybe Lake Geneva. You could sort of imagine yourself down here on the shoreline having a picnic. A beautiful, ideal place for life to exist. So Curiosity isn't able to find life, but ExoMars, the ExoMars rover, which is flying in 2020, which should arrive in 2021, this has actually got a more sophisticated drill on it than Curiosity. So actually when I said we might find evidence of life on Mars in 2030, we might actually find it a little bit sooner if we're lucky. So the ExoMars rover has a 2.5 metre long drill on it, and it'll be able to drill deeper into the Martian soil and sample sort of the rock which hasn't been affected by the incoming UV rays. So once the rover has drilled down about 2.5 metres, it'll be able to bring up a sample which has been undamaged by the sun's rays, and then using a technique called Raman spectroscopy, it might be able to detect life or the evidence of life. However, because it's a relatively simple rover in terms of what it can do, so it's by no means a simple piece of technology, but compared to what a human being can do, it is relatively simple. Basically, all this thing can do is take a sample out of the ground and then do a predefined analysis suite on it, which we decided on about 5 years ago. So if there's new advances in the technology within the next 5 to 10 years that would potentially be able to detect life, then this rover won't be able to find it. But there is the chance that it will be able to do it. So these are a couple of the places where the ExoMars rover might go. It might go to Marth Vallis. Marth is Welsh for Mars, so the Welsh Tourism Board will be interested to get on this. Or it might go to Oxia Planum. So the reason why it wants to go to Marth is because there are abundant clay mineral signatures that we've identified from orbit. Clay means water. There is evidence of volcanics there from satellite images, and also as well we have rivers which have been bringing in minerals as well. So in this one site there's about 3 or 4 places where we could potentially go and have a look at and sort of increase our chances of finding life. Oxia, I'm not so sure about. I've not worked on this area yet, but again, it's for similar reasons in that there are various there are iron, magnesium minerals there which could have potentially preserved ancient life. So our best shot actually for finding life starts in 2020. So NASA proposed the 2020 mission, quite similar to Curiosity, and this is part of a audacious 3-step plan for sample return from Mars. So in 2021, the NASA 2020 mission will land in one of the pre-designated landing sites. And what it will do, instead of analysing samples on the surface of Mars, it will actually drill down and take a core sample for later retrieval. It also has some certain instruments in there as well for sort of doing scientific experiments on the fly and also properly analysing sort of ideal places. So for example, if you land on the surface, you don't want to drill the first thing that you see. You want to sort of drive around and have a look for sort of the best area, sort of like the best part of the lake bed where conditions might have been favourable for preserving life. And then it's going to take a sample from there, and then it's going to drive to the next most favourable place and then take samples there. So we're going to end up with samples from Mars from hopefully 4 or 5 or maybe even 15 potentially different locations on the surface. So these are the potential landing sites. So there are currently 4 landing sites. In I think it's November, my boss Sanjeev will be going off to America, and he'll participate in the science argument, discussion, sort of affray, where they'll actually pare this down from 4 of these landing sites down to just 1 landing site where the rover will be launched. These are quite interesting debates, just because there's so much riding on these landing sites. So there'll be teams of people who have been working on, for example, Columbia Hills or Sirtis or Jezero, sort of trying to figure out why this is the best location to go to, and then there'll be disagreements and then much discussion and arguments about where exactly we should go. So Columbia Hills on the left, this has already been visited by the Spirit rover in 2003. It just arrived at the edge of the clay-bearing strata when the rover broke down. So we already know that there's minerals that could potentially host life there, so that's a good place to start. There's northeast Sirtis, where there are volcanic rocks. So they think that if they go and look in the volcanic rocks, there could have been fluid flow through the rocks driven by the volcanoes, and you'll have sort of a hydrothermally altered clays where there's the potential for life originating within the deep geosphere being preserved at the surface. There's Jezero crater, which has a river delta, which is where a river sort of flowed into a lake. So this is another lake similar to Gale crater. And then there's the joker in the pack, which is Midway. So Katie Stack-Morgan actually proposed that just because Jezero is just up the road from Sirtis, we could actually land the rover in between the two and then pick the best of which one when we actually get there, and worry about where to go exactly sooner we get there. So these are the potential landing sites. And then this is where it gets exciting. So in 2026, there will be a joint ESA-NASA mission where we will send a rover and a rocket to the surface of Mars. The rover, which is being built by Airbus UK in Stevenage, not a particularly exciting place I hear, but they do exciting things there. This rover, which hasn't been designed yet, is going to drive about 15 kilometres in 6 months, picking up all the samples that the 2020 mission has left. So if you just bear in mind that Curiosity has taken 6 years to drive 20 kilometres, this little solar-powered rover is going to do all that in a fraction of the time. This rover will then return back to the mothership, where it will sort of load the samples back into the rocket. They will then fire the rocket up into Mars orbit, a feat which has never been performed before. So this will be sort of exciting and new. And then in sort of 2028 or 2029, ESA will launch a mission which will fly to Mars. It will collect the samples from orbit and then return them to Earth. And then these samples will be returned and landed in Utah, as described in the ESA meeting, discussing how we're going to go about this. And hopefully it will return a small sample about this size, which will hold the answers of whether there was life on Mars. And our geochemists on Earth will be able to perform much more detailed analysis of these rocks than we'd be able to do on the surface of Mars. and hopefully yield whether there was life on Mars or not. Okay, thank you very much.